Remember that when building a regression model, we have a lot of choices to make in terms of what that model looks like. In this video, we're going to discuss the regularization procedure using the Lasso algorithm, which can help us automate some of these decisions. But wait, let's back up a moment and frame all of these new words in some context. Recall the story we've been following this unit. Our goal is to build a good predictive model of body fat percentage. Here we have data on 20 subjects and 19 possible predictors, including abdomen circumference, wrist, and 17 totally nonsense variables, which I simply generated using random numbers. If we use too many of these predictors, we risk overfitting the model to our data. If we use too few, we risk ignoring important information about body fat percentage and in turn risk poor predictions. Now there are three major model selection techniques that can help us out here. We've already discussed the first of these, variable selection, which identifies a subset of predictors that we can use in our model. We also discussed some drawbacks of variable selection techniques. Mainly, though they're nice and intuitive, they can produce misleadingly optimistic results. That is, they can overestimate the significance of the predictors and the magnitude of the relationship with the response. In this video, we'll explore an alternative set of techniques for model selection, shrinkage or regularization. In short, these algorithms perform model selection not by kicking some predictors out of the model, but by shrinking coefficients toward zero. Now there are multiple shrinkage and regularization methods. Since it achieves variable selection on top of regularization, we'll focus on the lasso. Finally, toward the end of the semester, we'll loop back to a third possible model selection technique, dimension reduction. To build up to the lasso, let's start back at the beginning. Recall that our goal is to estimate the population regression model of body fat percentage, y, using a set of available predictors, x. To this end, we use our sample data to estimate the beta model coefficients, denoted here by beta hat. When building this model, the residuals it produces are of central concern. For each case or subject I in our sample data, the residual is calculated by taking the observed value, yi, and subtracting the predicted value, y hat I, which is calculated by plugging into our model formula. Summing the squared residuals for all n cases in the sample produces the appropriately named residual sum of squares, or RSS. This measurement provides an overall measure of how far our sample cases fall from the model and is central to model building. For example, consider the standard least squares method, which is behind the models we studied in 155 and have been studying in 253. This method, which is used by the LM function, identifies the beta hat coefficient estimates, which make predictions as close as possible to the observed responses. Or mathematically, least squares identifies the coefficient estimates, which minimize the sum of squared residuals. For example, consider the simple model of body fat percentage by wrist circumference. The LM function identifies an intercept coefficient of roughly negative 75 percentage points and a slope coefficient of roughly 5 percentage points per 1 centimeter increase in wrist. The corresponding model R squared and sums of squared residuals are shown here. The total sum of these residuals squared is roughly 454 percentage points squared. Now, since these model coefficients were identified using the least squares method, this model minimizes the sum of squared residuals. The collection of residuals would be higher for any other model corresponding to any other set of model coefficients. For example, if we tried to use a slope that's bigger than that provided, we'd see that the overall collection of residuals would increase. Here, the residuals are indicated by these red lines. Similarly, if we try a slope that's too small, we also get bigger residuals. So least squares produces a line of best fit. It minimizes the sum of squared residuals, or the collection of residuals. This seems great, but let's consider a bigger model. Suppose we use the 20 subject dataset to build a model of body fat percentage using all 19 predictors, including abdomen, wrist, and the 17 nonsense predictors. The LM function returns a list of beta hat coefficients for each of these terms. Thus, including the intercept, there are 20 total model coefficients. Further, we know that by adding predictors to the model, even if they're nonsense, R² will increase and the residuals, or prediction errors, will decrease. In fact, since the number of model coefficients is equal to the number of data points, that is, we have 20 coefficients and 20 subjects, the R² is perfect and the error is 0. Okay, fine. But despite these measurements, we know that this model is far from perfect. It contains nonsense predictors and is no doubt overfit to our sample of 20 subjects. This discrepancy reveals a drawback of the least squares approach. Mainly, its simple criterion of selecting model coefficients that minimize the sum of squared residuals produces misleading, overfit models when lots of predictors are being considered. In cases where we're working with lots of predictors, the least absolute shrinkage and selection operator, or Lasso, algorithm provides an attractive alternative to the least squares method. Conceptually, just as we might think of Wonder Woman's lasso as reining in runaway villains, the machine learning lasso technique reins in runaway coefficients. The lasso builds upon the least squares technique. The idea here is that not only do we want to identify the beta hat coefficient estimates, which make predictions as close as possible to the observed responses, we want to do so while not overfitting the model to our sample data. To achieve this modified goal, the lasso utilizes a modified criterion. Specifically, it identifies the coefficients which minimize a penalized version of the sum of squared residuals. This combines the familiar residual sum of squares with what we call an added penalty term. Combined then, Lasso seeks both coefficients which produce small residuals and only have a small penalty. To understand exactly what is being penalized, let's pick apart this penalty term. First, lambda here is a tuning parameter that can take any non-negative value. At one extreme, when lambda is 0, this penalty term drops out of our criterion. Thus, when we tune lambda to 0, Lasso is equivalent to least squares. Next, the sum here adds up the absolute values of the coefficients of our p predictors. So, when is the penalty term large? Or what sets of coefficients are bad? For one, the penalty will be large when one or more predictor has a large effect on the response. That is, when one or more predictor has a coefficient that's large in magnitude. The penalty term can also be large if we have many predictors with tiny effects or tiny coefficients, where these tiny coefficients add up to a lot. Thus, though including all of these extra predictors with tiny effects might increase R² and decrease error, the penalty term will kick in and highlight that the inclusion of these terms increases the risk of overfitting our model to the noise in our sample. This property is what makes the Lasso algorithm shine. Now, it's certainly not obvious why this is such a big deal, so let's consider an example. We'll start with the Lasso algorithm, which uses a tuning parameter of lambda equals 0. The coefficients which minimize the penalized sum of squared residuals are shown here. And recall that when lambda is 0, Lasso is equivalent to the least squares algorithm. Thus, these coefficients are also the least squares coefficients. But let's crank up the tuning dial a little bit, increasing lambda to 0.0001. By picking a non-zero lambda, we're starting to penalize the total size of our model coefficients. Notice the impact of this penalty. Mainly, all of the coefficients in this second Lasso model have been squeezed closer to 0. So in each case, the abdomen coefficient is now closer to 0. The wrist coefficient is now closer to 0. The junk x3 term coefficient is now closer to 0. That is, each coefficient has shrunk. If we crank lambda even higher, to 0.01, we put an even greater penalty on the size of our coefficients. Thus, the coefficients shrink even closer to 0. In fact, the coefficients of two of our junk predictors have shrunk all the way to zero, thereby kicking these predictors out of the model. Now, let's pause here for an important detail that you might be worrying about. You might be thinking, predictors typically have different scales and units. For example, abdomens are certainly larger than wrists. Thus, a 1 centimeter increase in abdomen is relatively small. The corresponding change in body fat then, hence the abdomen coefficient, will also probably be small. On the other hand, a 1 centimeter increase in wrist is relatively large. The corresponding change in body fat percentage, hence the wrist coefficient, then might also be large. So that we don't punish predictors for simply being on different scales, Lasso standardizes all variables to be on the same scale with mean 0 and standard deviation 1. But this all happens in the background of the algorithm. When we actually see the Lasso results, when they're reported back on the original scale for ease of interpretability. So this is all happening in the background. What this means in the case of our model is that the two junk predictors that we just kicked out of the model are kicked out because they're crummy predictors, not because they have measurements on a different scale as the other predictors. As we continue to crank lambda to 0.1 and 1, the coefficients shrink even more, and even more of the junk predictors are kicked out of the model. By the time we crank lambda to 2, all of the junk coefficients have been kicked out of the model, and all that remains are our two meaningful predictors, abdomen and wrist. This is because the combined tiny effects of this large collection of junk predictors added up to a lot. Thus, we're penalized by the lasso. Of course, we bear the risk of going too far. At some point, if we tune lambda to be too big, all predictors are kicked out of the model and we're left with nothing. So clearly, picking the right lambda is crucial to implementing the lasso. So let's summarize what we've learned thus far. First, we know that lasso identifies the model, which minimizes a penalized sum of squared residuals. We also know that as lambda increases, our coefficients shrink toward 0. This is called shrinkage or regularization. We also know that picking tuning parameter lambda is a Goldilocks problem. We don't want it to be too big or too small. Rather, we want it to be just right. First, when lambda is 0 or too small, lasso is equivalent to least squares, thus doesn't simplify the model at all. When lambda is too big, it also kicks out not just the junk parameters or predictors, but the usable predictors as well. Now, why we want to get lambda just right is that when we do, Lasso helps build parsimonious or sparse models which only include the most relevant predictors, as we saw when we tuned lambda to 2. This is good because sparse models are less prone to overfitting. Finally, in class, we'll investigate how we can pick an appropriate lambda term using cross-validation. Finally, before concluding, let's consider how Lasso compares to our other regression techniques, including least squares and variable selection. First, relative to least squares, Lasso helps automate the model building process. Mainly by shrinking some coefficients to 0, Lasso also does variable selection. Lasso also wins what we'll refer to as a bias-variance trade-off. We'll learn more about this later in the semester. The idea is this. By shrinking coefficients, Lasso, you might notice, produces biased coefficients. But, especially when we have a lot of predictors, Lasso is also more consistent or less variable from sample to sample. And this gain in consistency is enough to offset the increased bias in our shrunk coefficients. What about Lasso relative to variable selection techniques, such as best subset and backward stepwise selection? Well, since Lasso doesn't perform multiple testing, it doesn't overestimate the significance of the predictors which remain in the model. That is, it's more reliable than the variable selection techniques that we learned earlier. Finally, Lasso isn't the only regularization technique. Ridge regression is another shrinkage and regularization algorithm. It also selects coefficients which minimize a penalized sum of squared residuals. However, the penalty term includes the sum of squared coefficients instead of the sum of absolute coefficients. Though this does the work of reining in the coefficients, ridge regression doesn't shrink coefficients to zero, thus cannot be used for variable selection. With this in mind, we're going to focus on the lasso. If you're curious, you can read the textbook, pages 221 to 222, for more rigorous geometric explanation for why lasso often shrinks coefficients to zero.